Welcome to Statics. I'm Dr. Stewart. Today we're going to do some examples for frames and machines. The example we're going to do is example 6.9 from Hibbler's statics book. With frames and machines, often we're asked to draw free body diagrams and to break up those frames and machines into multiple free body diagrams. And that's what we're going to do here. We're asked to draw the free body diagram for each member, for a pin connection, and for the whole frame that's given. Now let's look at this frame that we're given. This is a fairly simple frame. It consists of two members, a member AB and a member BC. Each of these members have external loading applied to them. Member AB has a coupled moment, and member BC, it has a concentrated force. These members are pin connected to each other at point B. And that's one of the points that we're going to need to analyze. The members are also pin connected to the ground at point A and C, respectively. So we've got a pretty good idea of how this frame kind of is constructed. Now let's go ahead and break that over to our knowns and unknowns. Let's say that our external loading, the M and the P, are knowns. Those are something that's given to us. And then let's analyze the joint connections and replace those joints with what kinds of reactions we would expect. These are all pin connections, so we're going to be expecting X and Y terms, and that's what we get. AX, BX, CX, AY, BY, CY. So now that we've kind of analyzed this a little bit, we got an idea of what things we might have to find. Let's go about creating our free body diagrams. Part A asks us to find the free body diagram for each member. There are two members, so we're going to create two free body diagrams. Let's start with the member on the left, which is member AB. We'll draw the line representing it, the beam. We'll put 2 points for A and B, and then we will replace our supports, our connection points, with reactions. So we replace the pin at A with an AX and AY, and we replace the connection point at B with a BX and BY. And here, we're assuming that AX and AY are positive sense. And then for equilibrium, we're going to assume that BX and BY are taking the negative sense. Now, this is an assumption. We don't know what their true senses are, but for equilibrium's sake, we're going to put them in that direction. Now, this is important because now that we've drawn our first diagram for our first member, let's draw the second diagram for the second member, for member BC. And in this member BC, we are going to transfer information from our first diagram into our second. Our two members are connected at point B, right? In the first one, we assume that BX is to the left and BY is down. In our second diagram, for equilibrium's sake, we need to choose opposite directions because the force is equal, but it must be in an opposite direction in the other member. So the BX we have here is now to the right, and the BY we have is now going up. Now this is key because when we go and analyze point B itself, we're going to need for these internal forces, the forces that are transmitted through point B, to disappear. So we've defined that sense. Now let's go and analyze our other connection point, that's point C, and let's replace this point C with reactions CX and CY. We'll try to be equal and opposite, so the CX here is opposite of the BX, but CY, we're going to have that going upwards. And that's because of the external loading that we have applied, it's needed to be going upwards. All right. So now we've got our two free body diagrams drawn here for our two members. And now the only thing that we might want to do is think about how these diagrams would respond or behave if we were to add them together, if we were to snap them together like Legos. Ideally, what we should see is we should have these internal forces equal and opposite, so they cancel out and they disappear when we get to our full free body diagram. Now let's go ahead and do the next part, which is examining this point B by itself. So the pin, that point B, if we examine it by itself and we take the forces that were equal and opposite from each of the free body diagrams, we can see that these forces are canceling out, that we did the right thing, that when we can examine this pin by itself, that those internal forces are equal and opposite, and the connection and the transfer of forces between the members. That's great. Now let's draw our free body diagram of the whole frame. Now this is the traditional free body diagram that we're used to. In this one, we take the entire structure, and the only thing we do is we replace those known external supports, so the pins at A and C, with the reactions. So AX, AY, CX, and CY, right? So now, in this full frame, if we analyze that point B, we see that those internal forces BX and BY, they do not appear. And so we've set up our free body diagrams correctly, right? Now, why is this important? Why is this process and making sure that these individual free body diagrams match up? Well, each of these free body diagrams can be used to craft equations of equilibrium. And those equations of equilibrium can be used to solve for unknowns, to solve for the reactions and forces that are transmitted through a structure. So we need to make sure that the free body diagrams, that their reference frames are consistent between each other so that our equations are consistent between each other. Well, that's our first example for frames and machine. I'll catch you next time in the next video.